A modern concrete highway bridge with severe structural cracks and steel rebar rusting through the surface. Hard cut to a massive, pristine Roman concrete dome completely intact, framed against a bright blue Mediterranean sky. So how did ancient engineers build structures that survive for 2,000 years, while modern concrete starts crumbling after 50? The answer isn't a lost magical secret. It's a violent chemical reaction, volcanic ash, and an accidental self-healing superpower inside the rock itself. Long before the Romans, early builders in the ancient Near East struggled to bond stones together without mud washing away in the rain. Around 6000 BC, Bedouin traders in the desert realized that burning crushed limestone in hot fire pits transformed soft rock into a reactive powder. When mixed with water, this burnt lime hardened into a solid, water-resistant floor. Imagine you're an ancient builder slaking lime. As water hits the chalky white rocks, the mixture violently boils and spits steam at over 200 degrees Celsius. But while these early mortars held simple walls together, they were still soft and brittle under heavy pressure or underwater. Enter the Roman Republic in the 2nd century BC, facing a massive demographic boom that required unprecedented construction. Roman builders needed a material that could set fast, support immense load-bearing arches, and survive submersion in ocean water for harbors. They harvested gray volcanic ash from the slopes of Mount Vesuvius near the Bay of Naples, known as pozzolana. When mixed with slaked lime, water, and volcanic tough gravel, something remarkable happened at the microscopic level. Diagrams showing silica and alumina from volcanic ash reacting with calcium ions to form dense mineral chains. This chemical bond didn't just dry out in the air, it actually hydraulic cured, setting faster and stronger when submerged underwater. By the time of Emperor Augustus, Roman concrete, known as opus caementitium, was reshaping the ancient world's skyline. Builders poured millions of tons of this heavy slush into wooden molds to create the massive Pantheon dome in Rome. To keep the dome from collapsing under its own weight, engineers graded the stone aggregate, dense volcanic basalt at the base, tapering to feather-light pumice stone at the top peak. Cutaway diagram of the Pantheon dome showing decreasing density of concrete layers from bottom to top. At 143 feet wide, it remains the largest unreinforced concrete dome in the world today. But the real miracle of Roman concrete lay underwater in harbors like Caesarea Maritima, built around 10 BC. Roman workers poured raw concrete directly into wooden caissons submerged in the ocean. Instead of dissolving or eroding, the salt water triggered a secondary chemical reaction with a rare mineral called aluminum tobermorite. Microscopic diagram showing ocean water flowing into microscopic pores, causing interlocking crystalline structures to grow. Instead of salt water destroying the material, the sea literally grew microscopic crystals that locked the concrete together tighter over centuries. For centuries, modern scientists wondered why Roman concrete had tiny white chunks scattered throughout its dark matrix. Scholars originally dismissed these white spots as poor quality control or bad mixing by tired Roman laborers. Close-up diagram of a millimeter-wide white lime clast inside a dark concrete core sample. But in 2023, MIT researchers discovered these were intentional lime clasts created through a process called hot mixing. Romans mixed quicklime directly with water and ash at extreme temperatures, preserving tiny pockets of concentrated calcium throughout the material. These lime clasts acted as a built-in automated repair kit. When a microscopic crack forms in a Roman wall, rainwater drips inside and hits the dry lime clast. Diagram showing water flowing into a crack, dissolving a lime clast into a calcium-saturated solution. The solution recrystallizes as solid calcium carbonate, sealing the crack completely shut before it can expand. While modern concrete with steel rebar expands, rusts, and cracks apart within decades, ancient Roman concrete literally heals its own wounds when it rains. From burnt desert limestone to volcanic ash, hydraulic harbor walls, and self-healing lime clasts, Roman concrete was an engineering masterpiece. Ancient builders didn't just stack rocks. They mastered material science to construct a civilization built to endure for millennia. Don't forget to like and subscribe for more deep dives into ancient engineering.